Example 5.9 or 6.9 for the textbooks given. For details, please see the description below. Consider an ordinary shower where hot water is at 140 Fahrenheit and is mixed with cold water at 50 Fahrenheit. It is desired that a steady stream of water to be 110 Fahrenheit to be supplied. Assume that the heat losses from the mixing chamber to be negligible and the mixing to take place at a pressure of 20 psi. We need to determine the ratio of mass flow related to the hot and the cold water. The first step is to write the mass balance. We have the mass going into the system minus the rate of mass leaving the system is equal to the change of the mass in the system. Since the system is steady, we could say that this value is equal to 0, and then we simply have that the mass going in, the rate of mass going in, is equal to the rate of mass leaving. The mass going in, we have the hot water and the cold water going in, and the mix is going to be leaving. So we have m dot 1, which is for the hot, m dot 2, that is for the cold, has to be equal to m dot 3. Now we're going to do the same process for energy. We are going to have that the rate of change of energy in minus the rate of change of energy leaving is equal to the change of energy in the system. Once again, this is a steady system, therefore this is equal to 0. The amount of energy going in, the rate of energy in, is equal to the rate of energy leaving the system. In this case, we are assuming that the heat is negligible. Therefore, the only changes that we're going to have are going to be the changes carried by enthalpy. So we simply write the amount of energy going in is the amount of energy carried by the hot water. So this is M1 and H1 plus M2 H2. And then what is leaving is the summation of the two masses, the two mass flow rates, times the value of H3. The intent of the problem is to find the ratio of the mass flow rate from hot to cold, which means that we have to do M1 divided by M dot 2. And we're going to label this with Y. Then we're going to try to rewrite this equation using this expression. So if we have this expression, we're going to divide everything by M dot 1. So if we do that, if we divide every single term in here by M dot 1, we simply have H1 plus M dot 2 M dot 1 H2 is equal to 1 plus M dot 2 M dot 1 times H3. And notice that we have this value already defined as Y, so we're going to replace it. H1 plus Y H2 is equal to 1 plus Y H3. And now what we need to do is find the values of the enthalpies at each one of the stages so that we could find the value of the ratio of the mass flow rates. In order to determine the value of the enthalpy, we first need to determine the phase of the water. If we go to table A5E, we see that for 20 psi, the value of the temperature, saturated temperature, is 227.92. This value is higher than any of the three working temperatures in the control volume. Therefore, for the 3 points in the control volume, the water is going to be considered to be compressed liquid. Therefore, we go to table A4 in order to get the values for each one of the temperatures. So if we go to 140 Fahrenheit, we see that the value for the enthalpy is going to be equal to 107.99. For 50 Fahrenheit, we see that the value is going to be 18.07. And for the mixing temperature, which is 110, we're going to see that the enthalpy is going to be 78.02. Now that we have the values for enthalpy, we are going to solve this equation for y, and then we see that y could be simply solved to be equal to H3 minus H2 divided by H1 minus H3. Now that we have all the values, we simply substitute 78.02 minus 18.07, and this is going to be BTUs pound mass, and then we simply divide by H1 107.99 minus H3, which is 78.02. Once again, this is BTU pound mass. This cancels, and that's exactly the unit we want. Since this is a ratio, it has to be unitless. And then if we substitute the values, we see that this ratio is going to be close to 2, which means that the value of the hot water has to be twice as large than the mass flow rate for cold water in order to be able to achieve a final temperature of 110 Fahrenheit.